Good morning. I hope you can all hear me. I can hear myself, so I think that's good. So, welcome to JC. My name's Ben Horton. I'm here with a company called SYENSQO. I'm going to be presenting to you our technology on out-of-autoclave products for large launch and space vehicles. But before I do so, some of you may not know who SYENSQO are, so I'll just spend a little bit of time maybe bringing you up to speed with SYENSQO, our legacy, and where we've come from. So I'll skip to those. So basically, SYENSQO really derives from a company called Solvay, which I hope certainly many of you will have heard. I think we were here at JC for the last number of years with a big Solvay stand. But we have legacy in space in particular that goes back to certainly prior to the 1970s, where we're doing a lot of ablatives for space structures that went into many of the shuttles that you'll have seen in the 70s from NASA, etc. So our background is right back from, I'll go to the slide, from things like cyanamide, ablatives early in the late 60s, early 70s. We also have a company called Advanced Composites Group. Then we went through SciTech, which you may or may not have heard of, SciTech Engineered Materials. That was spun into, made a purchase of a company called Umico. That was in the mid-2000s. The last acquisition was by Solvay in the mid-2010s, around 2015, 2016. And really in December of last year, what we decided to do was split Solvay into two groups. One group that was doing a lot more of the legacy work, and then SYENSQO, which is the company I'm working for now, that does a lot of our growth products. So we do composite materials, adhesives, specialty polymers, a lot of the specialty products. So that's where we are. From presenting today to you, really a small part of our portfolio. We have a very large portfolio that covers space, aircraft, automotive as well. But today I'm really talking to you about space and launch market, so where we are in that market, the history we have with space. As I was mentioning before, we have a very long legacy providing it to space market. Some of the challenges, particularly in the new structures and then the new way of delivering large payloads into space, and how to make structures at those large sizes. A bit on the increased use of composite materials with the space segment, and some stuff on really how we manufacture, what the advantages of going out of autoclave are for these structures. And then finally, a few of the solutions that we have for this market. As I said before, I will really be focusing on the out of autoclave for large structures. We do have a huge portfolio, and you're more than welcome to come visit us on the stand or speak to me afterwards about other products we have, such as ablatives, adhesives, etc. So maybe quickly on where SYENSQO sits. As I said, I'm part of our aerospace and defense market. We do have a whole market also that's concentrating on automotive and electronics as well. But within space and defense in particular, we provide products into the commercial aerospace, so products flying on Boeings, Airbuses, other large commercial transport. We're also a big supplier into the defense market, so the F-35, we provide products for that aircraft and a number of other aircraft as well. As everyone knows, the AAM, an emerging market, which we're certainly interested in focusing on, and we have some products that we supply into that market. Today I'm concentrating again on space and launch, so really launch vehicles for space, satellite, and even launch vehicles for defense. But we also have products that go into engines and propulsion as well. So, SYENSQO in space, it sounds like a bit of a tagline, but really wanted to show you, from the slide you can see here, that we have products going right back to Gemini and the Titan aircraft in, as I said, the 60s and early 60s, late 60s. So products in there such as ablatives, adhesives going into those products. Then we had the shuttle era, so I'm sure everyone's aware of the shuttle and the number of successful launches of that. We have products sitting in there, right through to today's market on things like the Vulcan rockets, which is certainly a current product, the Delta Heavy, and the SLS, which is a future rocket that should be flying soon. As I mentioned, again, you can see on the slide, ablatives, composites, adhesive bonding, those are all some of the products we use and manufacturing technologies that are going into these programs. But what are the unique challenges that you have in space or making products that are going to go into space? There are certainly some differences from making an aircraft or a large aircraft, which make the material selection very important. So maybe here we've got a slide that really compares maybe some of the requirements for space and launch against something like an aircraft structure. So some of this is fairly self-explanatory, but from a production point of view, spacecraft, you're not making hundreds of these a year. It's certainly a low-volume aircraft in comparison to an aircraft, and obviously against the car, the numbers are particularly low. But they are large, very large in size, and have some very specific requirements. You also have this design driver differences. So from a space and launch vehicle, for example, you're not really looking at redundancy. You're really looking at the static strengths, the performance of the aircraft for in general, single use. I know that some of the new aircraft now are looking to be reusable, but it's, again, not in the same level that you would for an aircraft, where you really have to have this fail-safe redundancy, high cycle fatigue performance. So there's some clear differences between the two requirements there. Some of the damage threats are also very different. So in space, you've got the manufacturing assembling actually is really where some of the damage can be incurred, whereas an aircraft, throughout its life, it's on land, ground, ground vehicles delivering food, people to the aircraft in and out. So there's a lot of opportunities there for damage and the environment as well. There's also some major differences around how you do a qualification for something like a space vehicle. So in general, again, for space and launch vehicles, you're doing proof testing, NDE on the parts that you're making to make sure that the parts are up to the standard required. Again, for an aircraft, you really need to do some rigorous damage tolerance and characterization on the aircraft. Surface environments are also very different. Space orbit, once you're in orbit, you haven't got the atmosphere and then the weather to deal with. That said, you still have all the problems of launch and making sure that your structure stays integral throughout the launch process. There are also radiation, et cetera, and other things to deal with in space that maybe you don't have to deal with quite so much within the atmosphere, but there are some major differences there. So some of the service environments challenges, in particular to space, are getting large masses into orbit. It takes a lot of energy to get that up there. These are large things, so you really need to figure out how to do that. Again, any structures that are going to be in space need to be stable under vacuum of space. And they will see extreme temperatures, from extremely hot temperatures to extremely cold temperatures, so that the range of temperature performance is different from that required for an aircraft. There is now, and increasingly, space debris that you may or may not have to deal with. Atomic oxygen, and the other big one, when you haven't got the protective atmosphere, is radiation and the ability for the material to survive in those environments. So as you move through time, I think the modern vehicles that we have today are using more and more composites in their structure, both in terms of the large components, for a number of reasons. And I'm sure many of you know all about composites. You're at JEC, but one of the main reasons here is weight reduction. Composites that does have opportunity to reduce weight over metals, and metals have certainly historically been used a lot more than the future aircraft. Structural efficiency, again, the ability to really tailor your structure, as everyone knows with composites, is a key part to this. You can put the strength and the weight where you need it with the composite structure. As mentioned before, again, thermal performance is also a key part to this. Once you get in space, you've got the really extreme temperatures, so you need a material that can cope with that. Composites also offer you design and customization. As I mentioned before, you can look at putting fibers in the right directions. And the other pieces on here are around manufacturability. So the ability to manufacture complex shapes and large structures that maybe you can't do or can't do as easily with metallic structures. It also gives you an opportunity here to reduce the number of parts in the aircraft. If you can make large parts out of autoclave, you can manufacture them integrally, which reduce your part count. So you can see here a number of really successful orbital launch vehicles that have composite materials. SYENSQO have a lot of products on all these aircraft, from the Electrons, the Alphas, Vega Cs, right through to the upcoming SLS aircraft. So, what kind of other structures that we make with composites today, and what are large structures in space? A lot of those are things like payload fairings. This is the part when you look at the rocket that really sits at the top of the rocket, where you have the expensive items. So, the satellites, the James Webb telescopes, those sort of things that have a lot of value. They sit at the top. As they travel through the atmosphere and deliver in space, they need to be protected from the atmosphere, so a large payload fairings that sit around the items. Those are then discarded, and the vehicles are launched from that structure. The other thing you have is fuel in these aircrafts, and a lot of that fuel is cryogenically stored, so we have cryogenic tanks in the aircraft. And then there are different rocket stages, so you need the adapters that hold the stages together and separate as those stages fall away. And finally, the rocket motor cases. So these are all very large structures. Some of these rockets are enormous, and really you need to be able to manufacture out of autoclave. Finally, an autoclave to manufacture these parts, and it is tricky. So why choose out of autoclave? Well, I've just mentioned size is certainly an important part, the ability to make large structures without a need for an autoclave that can cope with that, or secondary assembly of components. Cost efficiency as well. You know, an autoclave is not a cheap item to buy, although there are probably some people here that will sell you one. Getting one that's large enough for structure is not easy, and it's expensive. And particularly when you're doing things like one-offs, you know, you may not use that autoclave particularly efficiently as well. So part of this is really around cost efficiency. Energy consumption, again, autoclaves require a lot of energy. With out-of-autoclave technologies, you can really focus your energy and your heat and the way you heat the structure to reduce the energy consumption. Tooling as well, you can, if you're not in an autoclave and you don't have that environment, you can use some lower cost tooling and save money there to make sure. But really the key part here, I think, for out-of-autoclave and the key driver is the fact that you can make large structures, and that's why we're looking at that. So what does SYENSQO offer in this field is, as I mentioned, we offer a range of, we have a large product portfolio. I'm going to concentrate on 3 key products today, just to give you a little feel for what we offer for these structures. That said, there is a slide with a few additional products, and there are other products we have around ablatives, adhesives, etc. So if people are interested, are designing launch vehicles today and want to discuss that, I'll be available after the show here or on our stand. So certainly come and visit us, and we can discuss. So the first product we have is SYCOM 5320-1. Really, it's designed for use, so it can be used both within and outside of the autoclave. It's a toughened epoxy system, developed really for primary structure. So this is used on aircraft structure, but also applicable to the space and launch market. Has very good handling performance, so very long tack life and shop life at room temperature. So you can make large parts. You have time to lay them up. And make the part. It's got flexible cure cycles as well, so you can vary cure cycle depending on the properties and the equipment that you have, and it's suitable for complex parts as well. So good hot wet mechanical, very low void content, and mechanical performance properties, and this is key as well. You can get very similar performance from out of autoclave cure to that of an autoclave cured part. Available in a number of product forms, and I won't list them again. I think you all have access to the slides if you want to look at it in more detail, and we have product brochures on our stand if there's anything that is of particular interest to you here. But maybe one thing that hasn't been mentioned specifically, but I will focus on it, is also on these products we have NCAP database, so publicly available data for these products that you can use then for designing your components. So we have that both NCAP data, and we also have our own internal databases that we can discuss and share. The second product I'll present to you is, again, a toughened epoxy system. This is called MTM45-1. Again, a number of different curing temperatures that you can use, so different cure cycles with very high performance. It's a toughened epoxy system. Can be used both for vacuum bag processing and autoclave cure again, so multiple capabilities in terms of performance. It's quite a low density product, so actually over other even composite products, it offers a further 2 to 4% weight saving opportunity. And it's very excellent for damage tolerance. So very highly toughened system. Again, various product forms available on this product, and NCAP database and internal databases available as well. So I think that certainly is important when you're designing aircraft to have that information available to you. So, as I mentioned before, I think I may have skipped the slide then. Yes, so MTM46, sorry, is the third product I'll present to you today. Again, it's a epoxy system. It's also, but this one, where this one varies from the others is it's actually quite good for high rate production as well. So you can vacuum bag only cure it, you can autoclave cure it. But this product can also actually be used in press curing and some of our proprietary systems as well, which I'll mention. So. Flexible cure cycle, again, from 80 to 180 degrees. Killer flexibility, again, depending on the performance you need, there may be a requirement for post-cure. It's rate capable, as I mentioned, and DDF capable. So this is basically a proprietary process we have, which is called double diaphragm forming. And it basically allows you to automate the whole process from really the layup of the pre-preg to the finished part. It's used in press today, so you're limited by the size of your press in terms of the size of component you can make, but it's really interesting technology, particularly if you're looking at rate manufacturing, which may not be so applicable today in the space market, but for smaller satellites, for example, there'll be some opportunities there to use this technology. This has, again, a good press tack time in region of 30 minutes or under, and excellent performance to cost ratio. So this is one of our lower cost products, but high performance. It also meets NASA's outgassing standards when tested to the ECSS QST7002C, which some of you may not be interested in. So toughened system, flexible cure cycles, and high retention of TG under wet conditions as well. Again, I think on this one, we're looking to develop the databases, but if there's any specific data that people need, we'd be certainly happy to share that and discuss how to get that information together. So, I mentioned, I think you can see there's three topics, subjects, or materials that I've just mentioned on the slide, but we have a number of other systems that we are really targeting at the space and launch, and then the large part of those structures here. SYENSQO EP2190, again, a toughened system, NCAP database. We also have some Raven models available, so you can model cures and performance. We have SYENSQO 977-2. This is a really legacy product. It's used across a number of our customers in aerospace and space. It's been used by NASA in the past, so it has a lot of pedigree in space. It's been there. It knows that environment. This is an autoclave system, so you are limited by the size of your autoclave in terms of the size of the parts that you can manufacture with this. But certainly from a space perspective, it's got a lot of pedigree and experience. I won't go through the 5320-1 or the 45-1 and MTM46 again. I think I've covered those in a lot of detail. But SYENSQO 5250-4, this is a BMI. It's got higher temperature capabilities, number of different products in a number of different forms. Again, it's autoclave, but does offer, if needed, that additional temperature performance over our toughened epoxy systems. And last but not least is our APC2, which is a thermoplastic offering. So it's a reinforced thermoplastic product. We have PEC, PECAN, PPS, I think all available in different configurations, but this offers obviously potential for recyclability, good toughness performance, used in primary structures, and has fast cure cycle times as well. So those are really the kind of products that we're pitching today at the launch in the defense market. All of those pre-pregs today, but we do also sell things like resins for resin infusion if that's something that you're interested in for your design. So I think that was the end of my presentation as far as the slides are concerned. As I mentioned before, I've got my contact details here. I will be available after this presentation at the side. If anyone has anything they'd like to discuss, feel free to come and approach us. The other thing is we have a stand in Hall 5. I'm sure you'll see it. It's bright orange, as you can see by the screen, so it's fairly visible. There's myself and a number of my colleagues will be available to answer any questions on the stand. So feel free to come and visit us there. And We'll also, if you visit us later, we'll be having drinks, so you can get a drink and a coffee as well. So I hope it was an interesting presentation. I hope that you enjoy the show, and if there's anything else you want to discuss or ask, either visit me at site afterwards or visit us on the stand and speak to my colleagues. But thank you very much for your time, and enjoy the rest of the show.